Welcome to the AP Physics Workbook tutorial. This is Unit 10, Mechanical Waves and Sound. This section is 10.c, Superposition of the Wave Pulse. Here's the scenario. Blake holds the free end of a very light spring while the other end remains fixed to the wall. You're going to use the different representation for the different scenarios. For part A, Blake sends a wave pulse towards the wall, sketch the pulse, and as it continues back, and returns to Blake, and we're going to give an explanation on why. And here it goes up, hits the wall, then it's going to come back, but now it's going to be in reverse. So looks like this, right? Same amplitude. Then it's going to come down this way, right? Please understand the velocity is this way now. Okay, then it's going to come back to him like this. So it was just reflected. Okay, and I'm not going to write the explanation. I'm going to read you the notes for it. And this just comes straight from the textbook. This is the reasoning. Okay, so the reflection of a traveling wave at the fixed end of a stretched spring. Note that the reflect pulse is inverted, but the shape remains the same. Goes up, hits the wall, gets reflected, comes down, and the pulse is reflected to be inverted. The reason why, let's read it. Okay, whenever a traveling wave reaches a boundary, part of that wave is reflected. For example, consider a wave traveling on a spring that is fixed to one end. That's the one that we just talked about. When the pulse reaches the wall, it is reflected. Note that the reflection pulse is inverted. This can be explained as followed. When the pulse meets the wall, the spring exerts an upward force on the wall. According to Newton's third law, the wall must exert an equal and opposite downward reaction force on the spring. This downward force causes the pulse to invert or reflect. That's it. Next, here, this end, but this time it's not attached to the wall and it allows it to freely move. It's gonna come, hit it, and this should move up a little bit here. Then it's gonna come back down and the wave is going to still remain upright. And the velocity is this way. This time it's going to remain upright. Why? Let's look at the explanation. All right. So again, the pulse is reflected. The ring. So right here, the ring is then returned to its original position by the downward component of the tension of the spring. So notice it comes up, but rather than the wall exerting an equal and opposite force, the ring moves up due to the pulse coming in, right? And then as it comes back down, the pulse is still up. The reflection of the traveling wave at the free end of a stretched spring. In this case, the reflect pulse is not inverted. It is not inverted because there's no Newton's third law that the wall is exerting on. That's why it's not inverting. Next, these two students have a same wave that's going across to each other. And once it meets in the middle, it's going to something called constructive. It's going to combine. Then it's going to split apart. Okay. Ooh, you know what I'm going to do? I'm going to color code this for you. It might make a little bit more sense, okay? I'm going to make this green. I'm going to make this blue. And I'm going to make this green, okay? You might see this a little bit much better. So when it comes here, the blue is this much, right? Then the green is this much. So do you see how it combines? Then what goes along is going to be the green is going to be on this side now, and the blue is going to be on this side now. Okay, you see how it travels? Okay, then it reaches the end. So the wave that comes back to the left person was the right person's wave. Hopefully the color coding here helps you. All right, and I'm not going to write the explanation. I'm just going to read you the explanation. It comes from the book. All right, here it is. All right, so the explanation. Two wave pulses traveling on a stretched spring in opposite direction passes through each other. While the pulse overlaps, right here, it overlaps constructively. The net displacement of the string equals to the sum of the displacement produced by each pulse. Right? This is the idea of interference of a wave. When two or more traveling waves encounter each other while moving through a medium, the resulting wave is formed by adding together the displacement of the individual wave point to point. Waves coming together like this are said to be in phase and exhibit something called constructive interference. The visual that we saw here shows the constructive interference of two poles moving towards each other along a stretched spring. That's it. Next, this argumentation. Dominic watches what happens and she makes this argument. If the two wave pulses traveling in opposite direction along the same string meet, they reflect each other and go back where they come from. What is wrong and what is correct with that statement? So they don't reflect off each other in any way because there's no Newton's third law interaction between them. So the pulses just pass through each other unaffected because the pulse just add together while they overlap and they don't reflect. So if two phases travels in opposite direction along the string meet, okay, they don't reflect. So these two aren't reflecting. Okay, so they just go past each other. Do you see? The green doesn't go back. It doesn't get reflected. The green is traveling left and it stays left. The blue is going right. It stays right. So there is no reflection here. Okay, there you go. Those are your solutions.